The physical scaling of wind energy infrastructure is structurally limited by specialty chemical synthesis. High-performance turbine blades require massive quantities of epoxy resins derived from epichlorohydrin, or ECH. As shown in the stacked area chart, global production is undergoing a critical structural shift. Propylene-based ECH capacity contracted by 5.1% between 2021 and 2024 due to environmental regulations. Consequently, the market is increasingly dependent on bio-based glycerol pathways. At the same time, wind energy's share of global ECH consumption has more than doubled, rising to 22.5% in 2024. This creates a direct collision between decarbonization targets and chemical supply constraints. The dual pathway structure of ECH production exposes wind turbine manufacturers to complex feedstock volatility. As plotted on the dual-axis line chart, ECH spot prices peaked at $3,400 per metric ton in early 2022. This surge directly mirrored a 214.2% spike in crude glycerol, a byproduct of biodiesel refining. The bio-based ECH pathway is highly correlated with global biodiesel production swings, showing a correlation coefficient of 0.89. Meanwhile, the traditional propylene pathway remains highly sensitive to chlorine loop energy costs. A $100 increase in propylene feedstocks translates to a $165 increase in synthetic ECH production costs. This dual exposure leaves blade manufacturers highly vulnerable to external energy and agricultural shocks. The material bottleneck is compounded by the cubic scaling laws of structural wind engineering. As rotor diameters expand to maximize aerodynamic efficiency, blade mass increases nonlinearly. The horizontal bar chart illustrates this exponential physical progression. Scaling a rotor from 120 meters to 240 meters increases single-blade mass by over 400%. This physical scaling drives an exponential demand for structural epoxy. A single 240-meter rotor set requires 71.8 metric tons of epoxy resin, consuming nearly 24 metric tons of ECH precursor. Consequently, a 1 gigawatt offshore wind farm requires approximately 1,580 metric tons of pure ECH. This extreme material intensity makes global offshore wind deployment highly vulnerable to localized chemical supply shocks.